Greetings, ladies and gentlemen. My name is Mardel G. Borioso, your reporter for today, and in collaboration with my partner, Ms. Ana May Briones, we will be going to discuss the geological conditions necessary in the construction of dams, buildings, tunnels, and road cuttings. As future engineers, it is necessary for us to have initial knowledge in these regards for us to achieve a successful and durable project. Most civil engineering projects involve some excavation of soils and rocks or involve loading the earth by building on it. In some cases, the excavated rocks may be used as constructional material, and in others, rocks may form a major part of the finished product, such as a motorway cutting or the site for a reservoir. The feasibility, the planning and design, the construction and costing, and the safety of a project may depend critically on the geological conditions where the construction will take place. So I am assigned to discuss about the geological conditions necessary in the construction of dams and tunnels. So my first topic is about the geological conditions for the construction of dams. Dams may be defined as a solid barrier constructed at a suitable location across a river valley with a view of impounding water flowing through that river. The needs for dam involves hydroelectric power generation for irrigation purposes, to obtain water for domestic and industrial purposes, for fighting droughts and controlling flood, for navigational facilities, for the development of fisheries, tourism, and many more. The various forces acting on a dam involves its self-weight, water pressure, uplift pressure, earthquake forces, and other forces due to silt, wave, and ice.
Types of dams. The first one is a gravity dam, and one of which is the Grand Coulee Dam on Columbia River. It is a solid concrete or masonry structure that withstands the water pressure by virtue of its weight. All forces acting on this type of dam are assumed to be directly transmitted to the foundation rocks. They are generally of triangular profile and are among the safest. The second one is a buttress dam. An example of a buttress dam is the one located on Lower Colorado region. They have a continuous upstream face supported at regular intervals by buttress walls on the downstream side. They are lighter than solid dams. They are likely to induce greater stress of the foundation since most of the load passes through the buttress walls and is not spread uniformly over the foundation. Another types of dams are the arch dams. These type of dams are usually arch-shaped, convex at the upstream side. The major portion of the thrust forces acting on the dam are transmitted by arc action on the abutment rocks. Their structural efficiency are higher than that of gravity dams, since the presence of sound abutments is the prime necessity. They uses less amount of concrete. The last type of dams are the earth dams, and an example of it can be located at Manahadi or Crisa, which is the Hirakud Dam. These are non-rigid structures built with naturally available materials such as earth and rock. This type of dams are ideal where the dam site is weak to support concrete dams or where competent rocks are found at great depths. Here are the considerations that needs to be considered in the selection of sites for dams. Environmentally, the site where a dam is proposed to be placed and a reservoir created should not involve ecological disorder, especially in the life cycles of animals and vegetations and man. The fish culture in the stream is the first sector to suffer a major shock due to construction of dam. Its destruction may cause indirect effects on the population. These effects requires as thorough analysis as for other objects. The dam and the associated reservoir should become an acceptable element of the ecological setup of the area. Economically, the benefits arising out of a dam placed at a particular site should be realistic and justified in terms of land irrigated, or power generated, or floods averted, or water stored. Dams are invariably costly structures and cannot be placed anywhere and everywhere without proper analysis of cost-benefit aspects. Topographically, it would be a narrow gorge or a small valley with enough catchment area available behind so that when a dam is placed there, it would easily store a calculated volume of water in the reservoir created upstream. This should be possible without involving significant uprooting of population, loss of cultivable land due to submergence, or loss of existing construction. Technically, the site should be as sound possible, strong, impermeable, and stable. Strong rocks at the site make the job of the designer much easy. He can evolve best designs. Impermeable sites ensure better storage inventories, stability with reference to seismic shocks, and slope failures around the dam, especially upstream, are a great relief to the public in general and the engineer in particular. The slips, slides, and slope failures around and under the dam and susceptibility to shocks during an earthquake could prove highly hazardous. In terms of construction, the site should not be far off from deposits of materials which would be required for its construction. All types of major dams require millions of cubic meters of natural materials, earth, sand, gravel, and rock for their construction. Geological character for investigation. In this lesson, we will learn how the location and structures of dams in relation to the faults, dip and strike, and folded beds should be taken into consideration to be able to secure safety usage of the dams and to avoid failures in the future. Geology of the area. Preliminary geological surveys of the entire catchment area, followed by detailed geological mapping of the reservoir area, have to be conducted. This should reveal main topographic features, natural drainage patterns, general characters and structures of rock formations, such as their stratification, folding and faulting, and igneous intrusions, and the trend and rate of weathering and erosion in the area. Geology of the site lithology. The single most important feature that must be known thoroughly at the site and all around and below the valley up to a reasonable depth is the lithology. Examples are the types of rocks that make the area. Surface and subsurface studies using the conventional and latest techniques of geological and geophysical investigations are carried out. Such studies would reveal the type, the composition and textures of the rocks exposed along the valley floor, in the walls and up to the required depth at the base. Rocks are inherently anisotropic materials, showing variation in properties in different directions. Complex lithology definitely possess challenging design problems. Structures. This involves detailed mapping of planes of weakness like bedding planes, schistosity, foliation, cleavage, joints, shear zones, faults and fault zones, folding and associated features. Schistosity is the foliation in schist or other coarse-grained, crystalline rock due to parallel, planar arrangement of mineral grains of the platy, prismatic or ellipsoidal types, usually mica. It is considered by some to be a type of cleavage. While mapping these features, special attention is given to recording their attitude, spacing, and nature. Shear zones have to be searched, mapped, and treated with great caution. In some cases, this may be developed to such an extent that the rock may necessitate extensive and intensive rock treatment. Examples are excavation, backfilling, and grouting, and many more. Dip and strike. Dip is the acute angle that a rock's surface makes with a horizontal plane, while strike is the direction of the line formed by the intersection of rock surface with a horizontal plane. The strength of sound, unfractured stratified rock is always greater when the stresses are acting normal to the bedding planes than if applied in other directions. This being so, horizontal beds should offer best support for the weight of the dam. The resultant force due to weight of dam and the upthrust of impounded water is always inclined downstream. The most unfavorable strike direction is the one in which the bed strikes parallel to the axis of the dam and the dip is downstream. It must be avoided as far as possible. Therefore, other conditions being same, beds with upstream dips are quite favorable sites for dam foundations. In the figure shown in the presentation, both A and C are said to be safe condition. In the image A gravity dam is positioned on horizontal bedrocks, and in the image C, a gravity dam is positioned on upstream dippings wherein it is safe against resultant force. Whereas the image on B shows the resultant force positioned parallel to the bed strike and inclination of the rock formation, and the dipping of the rocks are downstream. This is said to be a very unsafe condition. Another geological character for investigation are the faults. These structures can be source of danger to the dam in a number of ways. Thus, the faulted rocks are generally shattered along the rupture surfaces. Different types of rocks may be present on either side of a fault plane. Hence, sites with fault planes require a great caution in calculating the design strength in various sections of the dam. Dams founded on beds traversed by fault zones and on major fault planes are more liable to shocks during an earthquake compared to dams on non-faulted rocks. So here's the images wherein the dams might be situated or located on varying conditions. For instance, in an undisturbed strata wherein dams are situated on horizontal beds. Another situation is dams being positioned on beds inclined in downstream direction wherein the inclination could be gentle and steep. There are also some instances wherein dams can be situated over folded beds, and wherein dams can also be located on beds inclined in upstream direction, or dams can also be situated over vertical beds, and lastly, dams can also be located or positioned over folded beds. In the image shown, there are some faults positioned that could be less harmful for the dams. My next topic is about the geological conditions necessary for the construction of tunnels. Tunnels may be defined as underground roads or passages driven through the ground without disturbing the overlying soil or rock cover. There are some chief classes of tunnels. We have the traffic tunnels, hydropower tunnels, and public utility tunnels. Purposes of tunneling may serve for facilitating rail and road traffic, for public utilities, for power generation, for mining activities, and for diverting water during construction. Here are some of the geological investigations that needs to be considered in constructing tunnels. Selection of tunnel route. There might be available many alternate alignments that could connect 2 points through a tunnel. The final choice would be greatly dependent on the geological constitution along and around different alternatives. Selection of excavation method. Tunneling is a complicated process in any situation and involves huge costs which would multiply manifolds if proper planning is not exercised before starting the actual excavation. And the excavation methods are intimately linked with the type of rocks to be excavated. Choice of the right method will, therefore, be possible only when the nature of the rocks and the ground all along the alignment is fully known. This is one of the most important aim and object of geological investigations. Selection of design for the tunnel. The ultimate dimensions and design parameters of a proposed tunnel are controlled, besides other factors, by geological constitution of the area along the alignment. Whether the tunnel is to be circular, D-shaped, horseshoe-shaped, rectangular, or combination of one or more of these outlines is more often dictated by the geology of the alignment than by any other single factor. Thus, in self-supporting and strong rocks, either D-shaped or horseshoe-shaped may be conveniently adopted, but these shapes would be practically unsuitable in soft ground or even weak rocks with an equal lateral pressure. Assessment of cost and stability. These aspects of the tunneling projects are also closely interlinked with the first three considerations. Since geological investigations will determine the line of actual excavation, the method of excavation, and the dimensions of excavation, as also the supporting system of the excavation, all estimates about the cost of the project would depend on the geological details. Similarly, tunnels passing through hard and massive rocks, even when left unsupported, may be regarded as stable. Assessment of environmental hazards. The process of tunneling, whether through rocks or through soft ground, and for whatsoever purpose, involves disturbing the environment of an area in more than one way. The tunneling methods might involve vibrations induced through blasting or ground cutting and drilling, produced abnormal quantities of dust, and last but not the least, interference with water supply system of the nearby areas. A correct appreciation of geological setup of the area, especially where tunnel alignment happens to be close to the populated zones, would enable the engineer for planning and implementing plans aimed at minimizing the environmental hazards in a successful manner. Thus, preliminary and detailed surveys are conducted.
The preliminary surveys for tunneling are the general topography of the area marking the highest and the lowest point, occurrence of valleys, depressions, bare and covered slopes, slide areas, and in hilly regions and cold climates, the snow line. The second one is the lithology of the area, meaning thereby the composition, attitude, and thickness of rock formations which constitute the area. The third one is the hydrological conditions in the area, such as depth of water table, possibility of occurrence of major and minor aquifers, and of simple type and of artesian type, and the likely hydrostatic heads along different possible routes or alignments. And lastly, the structural condition of the rock, that is, extent and attitude of major structural features such as folding, faulting, unconformities, jointing, and shearing planes if developed. Whereas, detailed surveys for tunneling involve borehole drilling along proposed alignments and up to the desired depths. The number of boreholes may run into dozens, scores, or even hundreds, depending upon the length of the tunnel. Rock samples obtained from the boreholes are analyzed for their mechanical and geochemical properties in the laboratories. The second one is the drilling exploratory, involving drilling shafts and adits, which allow direct approach to the desired tunnel for visual inspection, in addition to the usual advantages of drilling. The third one is the hydrological conditions. Driving pilot tunnels, which are essentially exploratory in nature but could better be used as main route if found suitable by subsequent enlargement. The actual number of boreholes and shafts and adits and their depth and length are decided by the length and location of the proposed tunnel. For tunnels with little overburden, this may be driven close to the proposed tunnel. Geological considerations in tunneling. Lithology. It has already been mentioned that information regarding mineralogical composition, textures, and structures of the rocks through which the proposed tunnel is to pass is of great importance in deciding the method of tunneling, the strength and extent of lining, and thus the cost of the project. In considering the lithology of the area, the consolidated and unconsolidated rocks should be looked upon too. These involve hard and crystalline rocks, soft rocks, and fissured rocks. The excavation in hard and crystalline rocks are very often self-supporting, so that these could be left unlined. A next round of blasting in the new phase created is undertaken, ensuring better advance rate. Rocks falling in this group include granites, diorites, syenites, gabbros, basalts, and all the related igneous rocks, sandstones, limestones, dolomites, quartzites, arkos, greywacks, and the like from sedimentary group, and marbles, gnesses, quartzites, phyllites, and slates from the metamorphic groups. When any one of these rocks is stressed, such as during folding, or fractured as during faulting, tunneling in these rocks proves greatly hazardous. Rock bursts, which occur during the falling of big rock blocks from roofs or sides due to release of stresses, or falling of rock block along fractures already existing in these rocks, often cause many accidents. In soft rocks, this includes shales, friable and poorly compacted sandstones, chalk and porous varieties of limestones and dolomites, slates and phyllites, with high degree of cleavage, and also decomposed varieties of igneous rocks. Their excavation cost, volume for volume, might be lower than those in hard rocks. Hence, temporary and permanent lining becomes necessary that would involve extra cost and additional time. Rocks like clays, shales, argillaceous and ferruginous sandstones, gypsum bands, and cavernous limestones have to be viewed especially with great caution during tunneling. Fissured rocks form a category in themselves and include any type of hard and soft rock that has been deformed extensively due to secondary fracturing as a result of folding, faulting, and metamorphic changes of shearing type. Another geological considerations in tunneling involves geological structures. The first one are the dip and strikes. These two quantitative properties of rocks determine the attitude of the rocks and hence influence in the design of the excavation to a great extent. There are three general cases to consider for the dip and strikes. The first one is the horizontal strata. When encountered for small tunnels or for short lengths of long tunnels, horizontally layered rocks might be considered quite favorable. In massive rocks, that is, when individual layers are very thick and the tunnel diameter not very large, the situation is especially favorable because the layers would then overbridge flat excavations by acting as natural beams. But when the layers are thin or fractured, they cannot be depended upon as beams. In such cases, either the roof has to be modified to an arch type or has to be protected by giving a lining. Sides of tunnels, however, could be left unsupported except when the rocks are precariously sheared and jointed. The second one is the moderately inclined strata. In the first situation, that is, when the tunnel axis is parallel to the dip direction, the layers offer a uniformly distributed load on the excavation. The arc action where the rocks at the roof act as natural arc transferring the load on the sides comes into maximum play. Even relatively weaker rocks might act as self-supporting in such cases. It is a favorable condition from this aspect. It also implies that the axis of the tunnel has to pass through a number of rocks of the inclined sequence while going through parallel to dip. In the second case, that is, when the tunnel is driven parallel to the strike of the beds, the pressure distributed to the exposed layers is unsymmetrical along the periphery of the tunnel opening. One half would have bedding planes opening into the tunnel and hence offer potential planes and conditions for sliding into the opening. The bridge action, though present in part, is weakened due to discontinuities at the bedding planes running along the arc. Such a situation obviously requires assessment of forces liable to act on both the sides and along the roof and might necessitate remedial measures. In the third case, when the tunnel axis is inclined to both the dip direction and the strike direction, weak points of both the above situations would be encountered. The last one is the steeply inclined strata. In rock formations dipping at angles above 45 degrees, quite complicated situations would arise when the tunnel axis is parallel to dip or parallel to strike or inclined to both dip and strike directions. In almost vertical rocks, for example, when the tunnel axis is parallel to dip direction, the formations stand along the sides and on the roof of the tunnel as massive girders. An apparently favorable condition, of course, provided all the formations are inherently sound and strong. Another geological structures that need to be considered are the folding, faulting, and joint system. Folds signify bends and curvatures and a lot of strain energy stored in the rocks. Their influence on design and construction of tunnels is important from at least three angles. Firstly, folding of rocks introduces considerable variation and uncertainty in a sequence of rocks, so that entirely unexpected rocks might be encountered along any given direction. This situation becomes especially serious when folding is not recognized properly in preliminary or detailed surveys due either to its being localized or to misinterpretation. Secondly, folding of rocks introduces peculiar rock pressures. In anticlinal fold, loads of rocks at the crest are transferred by arc action to a great extent on the limbs which may be highly strained. These conditions are reversed when the folds are of synclinal types. In such cases, rocks of core regions are greatly strained. Again, the actual regions of folds, anticlinal or synclinal, having suffered the maximum bending, are more often heavily fractured. The alignment of a tunnel passing through a folded region has to take these aspects in full consideration. When excavations are made in folded rocks, the strain energy is likely to be released immediately, soon after quite late to tunneling operations, where often causes the dreaded rock burst. Thirdly, folded rocks are often best storehouses for artesian water and also ideal as aquifers. When encountered during tunneling unexpectedly, this could create uncontrollable situations. The shattered axial regions being full of secondary joint systems are highly permeable. As such, very effective drainage measures are often required to be in readiness when excavations are to pass through folded zones. In case of faulting, fault zones and shear zones are highly permeable zones likely to form easy avenues for groundwater passage. Inclined fault planes and shear zones over the roof and along the sides introduce additional complications in computation of rock pressure on the one hand and rock strengths on the other. This discussion leads to a general conclusion. Wherever tunnel is intersected by fault planes or shear zones, it is to be considered as passing through most unsafe situations and hence designed accordingly by providing maximum support and drainage facilities. In the case of joint system, joints or cracks or fractures develop in rocks due to a variety of causes. Although all types of joints tend to close with depth, their presence and orientation has to be investigated. These are planes of weakness and must always be suspected when the rocks are folded and faulted. Even originally closed joints may become reactive and open up in the immediate vicinity of tunnel excavation. Jointed rocks cannot be considered as self-supporting, although these might belong to massive. The last geological considerations in tunneling is the groundwater condition. Determination of groundwater conditions in the region of tunnel project is not to be underestimated at any cost. In fact, groundwater level vis-a-vis tunnel access is a major factor governing computations of overhead loads on tunnels and also in the choice of method of tunneling. Groundwater conditions affect the tunnel rocks in two ways. Firstly, through its physico-chemical action, wherein it erodes and corrodes the susceptible constituents from among the rocks and thereby alters their original properties constantly with the passage of time. It might have already done much of this type of job when the tunnel is excavated through such water-rich rocks. Secondly, it affects the rock strength parameters by its static and dynamic water heads. Such an action may become highly pronounced when an artesian aquifer is actually intercepted by tunnel action. There are three general possibilities of relationship between the tunnel axis and the groundwater level. Number one, the tunnel axis may be passing entirely through impervious formations in which there is no possibility of water seepage or leakage or movement. It is an ideal condition for tunneling, of course, but is very rare in nature. Number two, the tunnel axis might be located mostly above the water table, intercepting the aquifer only in some sections. This is one of the most common situations and would involve provision for special drainage facilities to be located in water-bearing zones of the section. The head of the water in the zone of interception has also to be given due consideration and might necessitate lining for stopping leakage or inrush of water. Lastly, the tunnel axis might be located below the water table. Such a situation should be avoided as far as possible. In some specific cases, however, this might be the only possibility, such as in soft ground tunneling, underwater tunneling, for instance, below rivers and lakes, or in the karst regions.